Still it is lagging because
Yes, ma'am. Uh, can you hear me,
is
ma'am?
it? You are me clearly. Akshata, your voice is clearly audible.
Aarti ma'am, you are not audible to us actually. In between there, like too much lag is there and the voice is breaking it down.
Yes, ma'am.
Okay, fine. So, from how many classes is it happening, Akshata?
Which one, ma'am? Can like
This lagging voice?
uh this class, ma'am. Like last class, like there was a little bit lagging, but I think this class, like there is like too much of lag happening.
Okay, okay. Fine. Let me rejoin then. Is it fine now?
It sometimes it is fine, ma'am, but then again it starts. Like I won't be able to predict when it happens, but it happens.
I think now it's fine, Aarti ma'am. You can continue.
Okay, done. So let's continue the tech. And yeah, I was asking with which flow would you like to go for, Akshita? Shall I go with your level of understanding, or shall I move my syllabus as per the 30 classes schedule?
I think if we move by the 30 class schedule, I would be able to like at least see like more, like I will be able to cover more topics uh than the,
Hmm.
because if we are still stuck in one chapter, right? Then,
Hmm.
but in case if we move faster, I will try to understand more,
Hmm.
like I will try to make myself more attentive. If that helps, we can like finish more chapters, which will also be
Hmm.
helpful for me to practice more questions.
Hmm. So shall I move with the high flow? Is it okay with you?
Yes, ma'am.
Okay, done.
Or we can try that for like 2 classes, and if it's still difficult
Mm-hmm.
for me, I will like let you know. We can like try this
Done. Sure.
pace.
Okay, yeah, sure. Not an issue for me. Done. So I'm starting with this, and my next topic is Lorentz transformation. In Lorentz transformation, base scientist named as Lorentz, he had done the transformations, and we just need to check that what type of transformations he had sorted. Okay, so I will show you the same picture that we had collected in that Galilean transformation. Okay, let me give
Yes.
that particular picture to you, and then I'm explaining that picture to you. Yeah. Okay, have a look at this picture. Is it visible? The same picture I had given you during the Galilean transformation. Okay, so
Yes, ma'am.
basically to relate this, the measurements of one frame to another frame of Galilean relativity, basically we use the Galilean transformation. Okay, however, they do not give any correct answer that we try to transform the velocity of light also, right? We got a confliction in velocity of light, if you remember. So to make that assumption that the equations can be corrected by multiplying some constant gamma, then give that velocity of light, it must be same in all inertial frame of reference, isn't it? So we get the
Yes.
following transformations from S to S dash. And what was that? Basically, I had told you that my X dash should be Y, or I should say gamma, okay, X minus BT. So these are the is moving, and it is moving with this much of the velocity. And here the gamma basically is representing the speed of the light, that is 1 minus 1 under root 1 minus v square over c square. Done. So this is basically the Lorentz factor. It is known as, we add one Lorentz factor in this, that how is it getting transformed. So in Galilean transformation, what do we do? Add y dash, sorry, x dash equals to x plus vt, if you remember. But in
Yes.
Lorentz, we do this transformation. Okay, that is, we add a factor which is known as Lorentz factor gamma, and with that we subtract the distance, that is minus vt. Okay, now this can also be written in the terms of delta t also, and the distance between any two events can also be written as delta x. Okay, done. So vt can also be written in delta x terminology. So if I convert this x dash terminology, it will be delta x dash equals to gamma, okay, delta x minus v delta t. Okay, so I had just converted this form, considering delta x from x and delta t from t. Okay, so considering these two pointers, I had written this equation. Okay, similarly for delta t dash also, I can write that gamma delta t minus v delta x over c square. Done. So these are the two conversions. Okay, in this we show the distance and the time conversion specifically during the transformation. Okay, like I can give you one example for this, and after that we will move forward with something, some other topic. Okay, have a look over here.
Yes.
Okay, check. So this is the question. There are two inertial frames, S and S dash. Okay, their coincident time is 0 seconds, and they move apart with the, okay, as shown in the figure. So if an observer in S sees a balloon pop at 5 meters, okay, then at a time, let's say 10 raised to minus 8 seconds, then when and where did the balloon pop up as measured from the S dash? Have a look over here at the, that if an observer in S measures that at 5 meter of the distance, a balloon pop out at the time of 10 raised to minus 8 second. Understood?
Yes, ma'am.
Okay. When and where the balloon pop up as measured by S dash now. So we have to take out the answer in S dash form. Okay. So basically I am aware that my gamma factor is 1 minus under root 1 minus V square over C square. I'll put all the values. 1 over under root 1 minus, what is the value of V square over here? I guess this one is the value. So it will be 0.9 square C square over C square is how much? C square will be like this. Square will get cancelled out, and I will going to get the value something like 2.3 if I collect the result. Okay, now using Lorentz transformation from x, we know that our x dash is equal to gamma times x minus vt, right? This is what do we do, correct or not? So I can write it over here. This is 2.3, my x will be 5. Check how did I got 5 from here. From S, it is 5. Correct? So in
Yes,
S
ma'am.
frame, X is 5. Done. And this is minus 0.9. 0.9 already I told you from where did I got. 0.9 C it is. So I can write it 10 raised to 3 into 8. Correct? Multiply.
Yes.
Multiply 10 raised to minus 8. From where did I got 10 raised to minus 8? From here. Okay.
Yes.
So V
Yes.
into T. I had done this. So I got the answer nearly 5.29 meters. Understood or not?
Yes, ma'am.
Similarly, we will solve for T also. And my T dash is shown as gamma times T minus Vx over C square. This is the formula. Okay. Please remember these two formulas I had given you. First is this, second is this. Okay, this is about the uh, this transformation, what we are doing, Lorentz transformation. Okay, so here we have a Lorentz transformation question. So you have to put these two formulas. It is given in your formula booklet, don't worry. Okay, so
Yes.
2.3 10 raised to minus 8 minus 0.9 c multiply 5 over c square. Done. So this is what
Yes.
I have put. Now solving all this theta thing, I will get minus 1.15 into 10 raised to minus. Akshita.
Yes, ma'am.
Okay, great. Now after this, so basically we have studied here two transformations, Galilean and Lorentz. In Lorentz transformation, you have to remember these two formulas. That is, here the position and the time changes, whereas in our this part, that is your Galilean transformation, only velocity changes and it becomes u dash plus v. Correct?
Yes, ma'am.
Okay. Any doubts?
No, ma'am. I'll just write
Great.
down
Now
can I just write down the solution, ma'am?
formula. Yeah,
The
sure.
formula and the
Kindly be
solution.
quick.
Yes, ma'am.
Yeah, write down. Check. Is it visible?
Yeah.
Kindly be
Yes.
quick. Hmm.
Yes.
Are you done?
Yes, ma'am. I'm writing the solution, ma'am.
Mhm.
Yes, ma'am.
Okay. So now after this, we have another is known as. Okay. So moving ahead, our next topic is simultaneity. Simultaneity just tell us that in one frame, if any two events are occurring simultaneously and they look like they are occurring simultaneously, but in another frame, it is not possible that they would like to go as simultaneous activity.
Yes, ma'am.
Okay. Understood or not clearly?
Yes,
Okay.
ma'am.
Okay. Like I can give you one example. Wait. Basically here what did I told you that in any one frame, it's sometimes it looks like events are occurring simultaneously, but this thing is not possible in another frame. Okay, obviously in moving frame you will see those two events to be occurring at different times. Why? Because the light, if it is not reaching to you on time, then you will not see those two events to be occurring on a same time.
Yes, ma'am.
Okay. So here I'm giving you one example. Suppose we are having two trees which are observed from the S frame and here it is observed from the S dash frame. Okay. So from S frame, when I'm observing it, one tree is at the origin of the frame and the other tree is nearly 5 kilometers away. Done from the x-axis. Now, at the time of 4 microsecond, both the trees get hit by the thunderstorm. Right? Okay.
Yes,
Now
ma'am.
for the second observer, that is this observer, S dash observer, flying past 9, the lightning strikes will, yes, we have to calculate the time. Okay.
Yes, ma'am.
Okay, so now to calculate this time, we need to transfer the time of each strike in S to S dash. Correct or not? And our
Yes,
formula is T dash equals to gamma times T minus Vx over C square. Gamma is given as 2.3. Making sense?
yes, ma'am.
Okay, any doubts?
No, ma'am. So gamma is like standard, like uh
Yeah, if it is not given, it is standard. But
okay.
sometimes if they change the value of calculating gamma, I calculated gamma.
It's still 2.3, ma'am.
V is 0.9 C given. No, so
Yes,
here also it is given 0.9 C only. Check. Just
yes,
then, yeah, value is changing. Okay, done. So if the oak tree gets struck, let's say at t1 time, which is given as 4 microsecond, then the position obviously at x is to 0 in a particular first frame, right or not?
yes, ma'am.
Okay, so what will be my T1 dash? It will be 2.3 4 into 10 raised to minus 6 minus 0. Correct?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay, so I think when you solve this particular question, it will become 9.2 microsecond. Okay, now if it is, yeah, here is the thorough question. Yeah, so what I was telling is, if suppose the tree was stuck at t2 time, let's say 4 microsecond, but the position is now here, okay, at 5 kilometers from the x-axis, then what will happen? Then I will get t2 dash, what it will be, 2.3 to minus 6 minus 0.9 c into 5 into 10 raised to 25.3 microseconds. So what is the time dilation that we have faced over here? Did you understood what I had done?
Yes, ma'am. Yes,
Okay, so to
yes,
the observer in the rocket who is observing this activity, the tree was hit at 34.5 microsecond. That means adding these two. He is in the center, no? So it is this activity is happening pre and this is happening post, right?
yes, ma'am.
Done. So he will add the two timings because this is going in this direction. So it is moving away and moving towards, right? So 25 plus 9, when you will roughly get 34. Okay. So 34.5 microsecond before the oak tree. Okay. The observer in the rocket will observe that before this, he will observe this particular event and that will be at 34 microsecond before. Done. So remember that the observer in the rocket, the trees are moving to the left. Am I making sense?
Yes, ma'am.
Because the rocket is here, so this is left. Correct?
Yes, yes,
So for the trees which is moving towards the oak tree is basically moving away. This is what I told you now. It is going away and it is going towards.
yes, ma'am.
Okay, so the light therefore travels a shorter distance from the tree, this one, not this one, because it is going towards this, so the distance between them is small.
Yes, ma'am. Ma'am? Hello,
Yeah,
ma'am?
I'm not saying anything. I'm not
Okay.
saying anything. Yeah, I'm waiting
Sudden
for your
point.
answer. I'm asking, is it clear for you?
Yes, ma'am.
Okay. So if you want, you can repeat the same question, keeping it 100 kilometers somewhere away. Let's take speed as not 0.9, take 0.8 c. So you can check your answers also, that how you are performing. Done.
Yes, ma'am.
Okay. Now the next.
Can I just copy the question, the answer?
Yeah, this is what I am telling now. But that if you are copying, uh,
Or I can take the screenshot, ma'am. 1 second.
yeah, take it.
Yes, ma'am.
Done.
Yes, ma'am.
Okay, let's start the new topic, time dilation. So basically, Shita, to measure the time between any two events, we can use the Lorentz transformation. Okay,
Yes, ma'am.
isn't it? To
Yes, ma'am.
basically transform the time from start to finish and between them. Okay, so we have considered here two events which are occurring at the same place. Okay, and it is measured by an observer which is standing in the frame as. Okay,
Yes, ma'am.
okay. Let me show you one picture with respect to that. We will solve this question. Can you see this picture?
Yes, ma'am.
Okay, done. So basically, we are considering, let's say, two events over here, which is occurring at the same place. Done.
Yes, ma'am.
And yeah, which is occurring at the same place. It is measured by the observer who, isn't it?
What you said wasn't. I couldn't hear you, ma'am. You.
Yeah, I'm saying, yeah, is it audible now? I'm saying
Yes.
that a light at rest relative to the observer, sorry, we are considering here two events basically, which is occurring at the same place. Done. And it is measured
Yes.
by the observer who is standing in frame S.
Yes.
Okay. So let's take one example that the light at rest relative to the observer flashes at time t1.
Yes, ma'am.
The light at rest basically relative to the observer.
Yes, ma'am.
Okay. Yeah.
Yes, ma'am.
In S flashes at time t1 and then again at time t2. The first flash is time t1. The same. See, Akshita, it is continuously fluctuating. Then off, then again fluctuating. Then off, then fluctuating. This is the position of the light. Light
Yes,
blink, light off, light blink, light off, light blink.
yes, ma'am.
Then and off, then second blink. Understood or not? The
Yes,
picture.
ma'am. Yes, ma'am.
Now any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay, great. So here what I am telling is, so the time between the flashes measured in S is T2 minus T1.
Yes, ma'am.
Okay. And this is the proper time since two events are occurring at the same time in space. So can be measured by the same clock. I'm saying that at proper time, suppose these events are occurring in the space.
Yes, ma'am.
So it can be measured with the same clock only, no? Which is being used by the frame as, isn't it?
Yes, ma'am. Yes, ma'am.
Okay. The second observer, which is moving with some. Here it
Hello,
is.
ma'am.
Yeah, I'm saying where
Your
is the
voice
second
got
observer?
moving.
Now is it clear?
SV. 1 second, ma'am.
Hmm.
Yes, ma'am.
Hmm. So I'm saying this is the first observer which is doing the experiment on Earth. This is the second observer which is doing the experiment in space. Understood?
Yes, ma'am.
And he is at steady state, but he is in moving state.
Yes, ma'am.
Observe over here. Second flash you observe over here. Making sense?
Yes, ma'am.
Any doubt?
No, ma'am.
Okay. So according to him, from S frame, but from S frame, delta minus T1 dash. Correct?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. Let's we need to transform these times. So my T1 dash will be gamma T1 minus Vx over C square, correct?
Yes, ma'am.
Similarly, T2 dash is equal to gamma T2 minus Vx over C square, correct?
Yes, ma'am.
Hence, my T2 dash minus T1 dash will be gamma T2 minus Vx over C square minus gamma. Tell me the doubts.
1 second, ma'am. Just go through the equation.
Uh-huh. Please.
Yes, ma'am.
Done. So
Yes.
basically, the position which is measured in Sx is the same for each flash. Okay. So what is my T2 minus T1 dash? It will be gamma times T1 minus T2.
Yes, ma'am.
Okay. So therefore, my delta T dash formula comes gamma times delta T. This is the formula for time dilation for calculating. Okay. Gamma is basically always greater than the one value. Okay. Which means that the observer moving relative to the flash will measure longer time. Very short, I will tell you speed equals to distance. So more distance, this one. So who will catch the time? This one. Okay.
Yes, ma'am.
Understood or not?
Yes, ma'am.
Okay. So basically what happens here is gamma value is always coming greater than 1. So it simply implies us that the observer moving relative to the flashlight will measure a longer time between the flashes because his speed is very, very high. Na? So the speed is high, the time will become less. So if time is high, the speed will become less.
Yes, ma'am.
Okay. Yeah.
Yes,
And the flashlight is traveling more distance because he is observing the event happening from the space, right?
yes,
So the flash time will be measured to be longer, okay, from the moving frame. This is known as time dilation, whose formula is time equals to gamma times T naught or delta T dash equals to gamma time delta T, where your T naught is the proper time.
yes, ma'am.
Now, what is proper time? Which is the observer measures it with the same clock. Okay.
Yes, ma'am.
Okay. Now, next topic is contraction. Now, what is length contraction basically?
Hello, ma'am.
Yeah, hello. I'm just checking. I'm here only. Don't worry. I'm just checking that what topic is going on. Yeah. So in length contraction also the same event that you are observing, okay,
Yes, ma'am.
that is, I'm talking about event, okay. I'm talking about this particular event. Basically, what happens is the length of the body is the difference in the position of its ends. Okay.
Yes,
So
ma'am.
basically, what happens is the proper length changes. Okay. The proper length is what? This is the rod. Check. Here it is a rod. Okay. And one person is observing from extreme, one person is observing.
Yes, ma'am.
Measured by both of them. So proper length will be measured by, am I audible?
Uh, kind of, ma'am. Like, you're not always audible, ma'am. Like, I think today, like, there are lots of, like, uh, your voice is, like, kind of going and coming back. Like, a lot. It's like,
Okay, okay, okay. Wait, let me just check. Okay. Is it clear now?
yes, ma'am.
Okay. So basically, what I'm telling is that of the body is basically
Again, it went, ma'am. Like, when you speak, it is coming. But when you speak, like, very, like, uh, fast, the voice kind of goes back. And then it again
wait,
comes.
wait, wait. Yeah, okay. Just give me 1 second, Akshata. I'm rejoining.
Yes, ma'am.
Am I audible now?
Yes, ma'am. But when you said audible,
Okay.
right? Like the audible, the thing just broke into audible, like that. And then when you speak fast, like, I think, like, from your side, the network connection, like, is bad now.
I'm not able to recognize because from here it is going well. I can able to, yeah, maybe due to that only it could be a technical glitch.
Yes,
But
ma'am.
whenever it's going, just do let me know. Sometimes even I keep my laptop little bit away, so the voice becomes a little bit low. Okay.
Okay, ma'am.
Yeah, while writing now, sometimes I keep my laptop away.
Yes, ma'am.
That's why maybe. Okay. So coming back to the pointer, I was telling that the length of the body is what? Its final position minus its initial position. Okay.
Yes. Yes, ma'am.
Understood?
Yes,
Done.
ma'am.
So basically from the frame S dash, you can be writing x2 dash minus x1 dash.
Yes,
That is
ma'am.
your delta x dash.
Yes,
And
ma'am.
similarly, the proper length will be your delta x, that is x2 minus x1. This is for
Yes.
the S dash frame, and this will be from the S frame, correct?
Yes,
Okay.
ma'am.
The observe it as x2 minus x1. Now I am transforming all the things. Okay, so my x1 dash will be gamma x1 minus vt, x2 dash gamma x2 minus vt. So my x2 dash minus x1 dash will become gamma x2 minus vt minus gamma x1 minus vt, correct? So my, am I making sense?
Yes, ma'am. Yes, ma'am. I can hear you.
Okay. Yeah. So similarly, both the
Ma'am, now again the voice went. Hello, ma'am.
yeah, hello.
And now it came back.
Yeah. So I'm saying, as per this, I can convey that my x2 dash minus my x1 dash is gamma x2 minus x. Making sense? Hence, x dash equals to gamma times x.
Yes, ma'am.
Okay. So this could be the formula. Same way that we had done delta x from the specific thing. So you can write it as 1 by gamma times delta x dash, correct? Or even you can write it as x2 minus x1 equals to 1 over gamma x2 dash minus x1 dash. Okay?
Yes, ma'am.
Any doubts?
No, ma'am. I'll just I'll just take the photo, ma'am. Can you zoom out a bit of
Yeah, wait. Yeah, wait. I'm doing.
uh like yes, yes,
Check. Is it visible?
yes, ma'am.
Okay. So basically what I was telling is, sorry. Yeah. So coming back to the point, this particular thing I can rewrite it as it is L, and this is L naught times gamma. Okay, done.
Yes, ma'am.
Okay, so now let's do the addition of the velocities. This done, time is done. So now addition of velocity. So what is the addition of velocity? Say it simply say u dash equals to u minus v over 1 minus u v over c square. Okay.
Yes, ma'am.
Yeah, this is the particular formula for addition of velocities. Okay, just remember this formula. This to we are aware, right? The final
Yes, ma'am.
velocity minus initial velocity. 1 over uv over c square. This is what you have to add.
Yes, ma'am.
Now measuring light. From this formula only I will measure the speed of light. Okay. So what does this formula convey? So let's check. I'm showing you one picture. Okay, Akshita. So as per this picture, who is standing in S? Okay, it shines a light and measures the speed of the light at which it propagates in the X direction. Okay, and he measures it to be C. Correct? Now,
Yes, ma'am.
let's use the Lorentz transformation to check in S dash frame. Any doubts?
No, ma'am.
Okay. So as I had told you that my U dash is U minus V over 1 minus UV over C square. Okay. Done.
Yes,
Where
ma'am.
from S frame, my U value is nothing but C. Correct?
Yes, ma'am.
Okay. So therefore my U dash will be C minus C. I had just put, in spite of U, I had put C. Nothing else I had done.
Okay, ma'am.
Okay. Yeah.
Yes.
So further minus V over C, because one C will get cancelled.
Yes, ma'am.
Done. Any doubts?
No, ma'am.
Okay. So U dash, you will get C will come out. Okay. As a common thing. So it will be 1 minus V over C over, if I take it,
Your voice again. It is not. It's not audible.
am I audible now?
Yes, ma'am.
Okay. So I am saying from both the frames now converting Lorentz transformation. Okay. While going through Lorentz transformation, now you can check, Akshita. In S frame also the value is C, and S dash frame also the value is C. Any doubts?
No, ma'am.
You want to ask anything?
No, ma'am. No, ma'am.
Sure.
Yes, ma'am.
Oh, okay. You can take the picture of this.
I took, ma'am. When you zoomed out, I took it.
Okay. Okay.
Yes.
Let's see. I'm sitting outside if you get a correct network or good network. Okay. Yeah. So let's do it again from the next point. Okay. So this was last topic for this chapter. Muon. So I'm doing muon experiment for you now. This is very important. Many a times it came exam. You will get particular chapter in.
Ma'am,
Okay.
your voice again went, ma'am. Like, yeah. I heard
Now is
some,
it?
but I didn't hear anything else.
I'm saying, yeah, I'm saying that the particular videos and question answers you will get from paper 3 for this.
Yes, ma'am.
Okay. Now let's do the muon experiment, and it's a very important topic. What happens here is you just have to listen. Okay, don't worry. So rockets basically traveling close to the speed of light. Okay.
Yes.
Happen is it is worth looking at some results from the actual experiment with the particles that really do travel that much faster. Okay, rockets are traveling close to the speed of light. It seems a little bit far fetched, correct?
Yes, ma'am.
Okay, so that means it is worth of looking at some of the results from the actual experiment with particles that really do travel that much faster.
Yes, ma'am.
Okay, so now muons are produced in the upper atmosphere as a result of the deep.
Can you repeat, ma'am?
Yeah, sure. I'm saying that
Mm.
muons are the particles. Okay. Muons
Yes.
are the particles that are produced in the upper atmosphere. Okay.
Yes, ma'am.
Due to the decay of pions.
Yes, ma'am.
Pions are basically released by cosmic rays.
Yes, ma'am.
What are cosmic rays? The rays which are coming from the sun.
Yes, ma'am.
Okay. So they travel at the speed of Akshita. They travel, the muon travel at the speed of 0.98 times C. Okay. And they have a half-life of 1.6 microns.
Yes, ma'am.
They can be detected via Geiger Moller counters on one over the other. Like that they can be seen. Okay. Because they
Yes.
travel very, very fast, that they appear that they pass through the tube stacking over each other. Understood?
Yes, ma'am.
Okay. Now, if suppose I consider 100 muons, let's consider 100 muons. Okay. Suppose they are kept at a height of 480 meters. Okay. Now,
Yes.
as they travel to the earth, they will decay because 100 muons are detected and they are detected from the ground.
Yes, ma'am. Hello, ma'am. Ma'am.
Am I audible? Yeah, hello.
Yeah. Yes, ma'am.
Hmm. I'm saying, suppose they are traveling with the speed of light, still they will take 1.6 microseconds to reach the earth's surface.
Yes, ma'am.
Whereas their half life is how much?
1 point.
1.6 microsecond.
Yes.
Yeah, so basically they will not be observed from the earth's surface. Understood?
Yes, ma'am.
So non-relativistic physics say that at this time the half of the muons should get decayed and only half be visible. So as I had taken 100 muons, I will see correct or not.
Yes, ma'am.
But according to special, the time in the muons that they are traveling, and if suppose they get dilated, okay, from the frame of reference, okay, then their half life could be made longer by this much time. Okay, as per special relativity, okay, the
Yes, ma'am.
time in the muons, that is the frame of reference is dilated so that the half life could be made longer. Understood or not?
Yes, ma'am.
Like we are just elongating their time interval. Let's say my gamma is 5 over here. Let's say my T naught is proper time of the half life. Okay, and my T is the measured half life from Earth. Okay, so let's say the measured one is 8 microsecond. Okay,
Yes.
and they are traveling at the speed in the time in 1.6 microsecond down to the Earth. Okay,
Yes,
so
ma'am.
what is the formula to find out? N equals to n naught e to the power of minus lambda t. Okay. So if I apply all these factors over here, I will get nearly 8 out of 100. Understood?
Yes, ma'am.
Okay. What I am doing here is exactly I am delaying their time interval. Akshita, I am delaying their time interval as per special relativity.
Oh, Okay, ma'am.
Okay. So if I'm
Yes, ma'am.
delaying their time, that means 87 I will get rather than getting 50. Because see, their half life is 1.6. Okay, they are traveling with 1.6. Now, if their half life is 1.6, then out of 100, half will get decayed till they reach the surface of Earth.
Yes, ma'am.
But as per special relativity, if I delayed that actual timing, then 87 I can save.
Yes, ma'am.
Okay.
Yes,
So
ma'am.
basically, what is, if suppose we take a look at this in the frame of reference of the muons, suppose here is a muon coming, and I am standing in this frame of reference only. Okay. And they will decay in 1.6 microseconds. Okay. But the distance to the earth will be contracted. Here is my earth. I had contracted it because speed equals to distance over time. So I'm shortening the distance so that I can increase the time. Are you getting?
Yes, ma'am.
Getting?
Yes, ma'am.
Akshita?
Yes, ma'am.
Akshita, are you there?
Ma'am? Ma'am? Ma'am?
Yeah. Yeah, relax, relax. I'm here. Am I audible?
Yes, ma'am.
Yeah. How much you have not heard?
I think I heard this part. Like
Heard,
the
no? Okay.
yeah.
Yeah, I'm saying I'm contracting the distance between Earth and the muon so that I can increase my time. Okay. So let's do that. L equals to L naught over gamma. L naught is 480, the actual distance. I am putting a factor 5. So I will get 96 meters now. I will not get 480, but I will get 96. Okay.
Yes, ma'am.
I told you, no, it is kept at a height of 480 meters.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. And I had given you the value of gamma as 5. I had just
Yes.
put the two values over here and I had contracted it to 96 meters as per
Yes, ma'am.
Lorentz transformation.
Yes, ma'am. Hello, ma'am.
Yeah. Hello.
Yes, ma'am. I can hear you now.
So now this time is very much less than the half time, which was, if you remember, 0.9 1.6 microseconds. Remember what was the half life? 1.6 microsecond. This is
Yes, ma'am.
much lesser than this.
Yes, ma'am.
Correct?
Yes, ma'am.
Okay. So now I have shortened the time. I have shortened. I can contract the length. I can delay the length. I can delay the time. I can shorten the time with the help of Lorentz transformation. Okay. So that I will be getting 87 remaining, not 50. Understood? So
Yes,
this
ma'am.
result of muon experiment agree with those predicted by Lorentz transformations. Any doubt?
No, ma'am.
Okay. So this chapter is over. Akshita, we will start
No, ma'am.
our new chapter, that is B1 from. Okay.
Yes, ma'am.
Akshita, and it is my humble request that you will study the graphical representation of all the things I have taught you today.
Okay, ma'am.
Okay. Graphical representation is little bit, it's not